Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Lecture 90, energy and waves. We're going to talk about energy and waves now. Now remember that we had said that waves transfer energy and momentum, but not mass, right? Or not matter. So it's a little bit funny to think about, well, what is the energy in the wave? Okay, so that's what we're going to discuss today. And to kind of set it up, I want to imagine that I am putting energy into this system, right? So this would be power, of course, because I'm doing it continuously. So I'm putting in a certain amount of energy per unit time. So some number of watts I'm inputting into the system by wiggling this piece of string. Yes?
Yeah.
But let's say that I just started doing this, right? And so we have energy in this part of the wave here, right?
Yeah.
But not in this part of the wave, because this hasn't received the wavefront yet, okay?
Okay.
So there's no energy here, but there is energy here. But it's traveling to the right with the wave speed v, right? So if I wait a little bit of time, say delta t, after this point, now all of a sudden we'll be putting more energy into the wave, right? So across this boundary, this region over here will now have wave energy in it, right? The string will be bouncing up and down just like it is over here. So how much energy did I put in, right? Well, if I assume that this hand is providing a certain amount of power, right? So this is kind of the energy density, right? So in a string, you know, imagine the string is really, you know, a three-dimensional object, so it has a cross-sectional area in the string and all that, right? So we're really talking about an energy density. So that's the energy per unit volume that's being put into the string times the volume of this new little element over here. So we'll say that it is the cross-sectional area A of the string times the velocity, the wave velocity, times delta t. Yes?
Yeah.
Okay?
Okay.
So I know it seems like we haven't actually calculated anything, we just kind of put a lot of words up there, but we're working towards that, okay? So at this point, though, we assume we know all these things. And so what I want to do now is I want to divide both sides by delta t, right? Because delta E over delta t, right? What is that? That's energy per unit time, right?
Yes.
What do we call energy per unit time? Power, right?
Yes.
And specifically, it's the average power. So that will be equal to eta times A times the wave velocity v. Well, if I divide this power by area, now I have like a measure of power per unit area, right? So I'll take P average divided by the area, right? That is going to be equal to eta times V, right? So what do we call this? We call this intensity. You've probably heard the word intensity before, right?
Yeah.
Like, you know, what is the intensity of that laser or something like that, right?
Yeah.
And so what is it? What is intensity? It's a measure of power per unit area. The sun, right, is a certain distance. It's a certain average distance away from the Earth, right? And it provides a relatively constant amount of power to the planet. So if I were to walk outside, right, and measure how much energy per unit time, or power, is received per square meter, right, that would be a measure of the intensity of the sun, you see?
Yeah.
And so I think it's called the spectral constant. And so the intensity of the sun, so I'll write I sub sun, but this is also at Earth, right? So I'll put comma E for Earth, right, is equal to, I think it's 1.35, yeah, 1.35 times 10 to the 3 joules per second per meter squared. And we are, of course, not very close to the sun. In fact, we are about 93 million miles, okay? So let's talk for a minute. What happens when we radiate energy out into space, or power out into space, right? It kind of travels in all directions, right, at the same speed, right? So it looks like an expanding sphere, right? So we've talked about these kind of waves before, but you can also have spherical waves. Think about a surface wave where you throw a rock in the pond, right? It doesn't exactly look like the little waves that we draw here, right? But if you imagine this in all directions in a plane, right, that's kind of a sphere or a surface wave, right?
Yeah.
You can do the same thing in space, right, in all directions, and it expands out like a sphere, right? Does anyone know the surface area of a sphere? You may not, I mean, unless you've encountered it. The surface area of a sphere is 4 pi r squared, okay? So if you want to know what the intensity is at some distance, call it r, right, it's equal to the intensity at the source, right, divided by 4 pi r squared. This would be appropriate for something like the sun, okay?
All right.
if like a speaker, for example, which we'll consider at the end of the lesson today, we'll talk about a set of speakers in a rock concert, okay? Speakers radiate energy in a different way. They radiate it in a hemisphere shape. So it's like half a sphere. So you'd use half of this surface area. So it's it'd be the intensity divided by 2 pi r squared, okay? So it only radiates it in half of a sphere direction, if that makes sense. Yes?
Yeah.
Okay. So this is the spectral intensity on Earth, and we are 93 million miles away, right?
Yeah.
What do you think the spectral intensity is on Mars? And Mars is, I think, 142 million miles? Yeah, 142 million miles from the Sun. Well, if we think of the ratio of, say, intensity, actually I'm going to write it like this. This is kind of how the astronomers would do it, I think. I think the symbol they use is a circle with a dot. That means sun, okay? I sun, comma, Mars divided by I sun, comma, Earth, right?
Yeah.
Notice that it's going to, whatever this is, right, it's going to be the ratio of these two, of this, right?
Yeah.
So it would be the intensity at the source, right? The 4 pi's will cancel, right? But we'll get R Earth over R Mars squared times I. I just call I. Oh, well, we haven't done that yet. So I can then multiply times the intensity at the Earth, right? And I should be able to compute that, right? So this is 93 million miles divided by 142 million miles. We'll square that times I at Earth, and that will be equal to, somebody punch it in the calculator. So 93 divided by 142, and then square that value.
It's 0.42, 0.43 actually.
Okay, so 0.43 times I at Earth, right? So that means that it's 43% of the spectral intensity on Mars as it is on Earth. So if we wanted to do some solar-powered stuff up there on Mars, we'd better take into account of the, significantly lower spectral intensity, right? Does that make sense so far? Right? So we've really just, all we've done is we've introduced some new concepts, right? We've got a concept of energy density, eta here, which is the energy divided by the volume, right? It's how much energy you have in a volume of material, right? So here we were thinking, well, whatever the volume of this string is, right? That's its cross-sectional area times its length, essentially. We're assuming these amplitudes are small, right? Such that the total displacement delta x here, right, or v delta t, is equal to the length of the string, right? Times its cross-sectional area, and that would be true if it was a small amplitude, right? Really big amplitudes is totally not true, but small amplitudes it's true, roughly, approximately, okay? So we're assuming what the energy density is here, and using that to figure out how much we're adding based on the input power. So where's the power coming from? It's coming from the hand, right? The hand is the thing that's putting the power in, yes?
Yes.
Okay. Putting the energy in, okay?
Okay.
All right, so now I want to look at, well, let's relate these quantities that we've come up with here to a simple mass on a spring kind of oscillator system. Okay, so you might recall that the energy of just a simple harmonic motion of a mass on a spring, right, or something like the energy was equal to 1/2 times the mass times omega squared times, we'll call it y naught squared, right? That's just the amplitude of the oscillation, right? We can just call it y, I guess. So, but now I want to consider, a continuous system, right? So instead of writing some mass, I want to really consider a little bit of, I'll call it a delta m, okay? And that delta m is equal to rho times some delta v, right? So rho, that's the mass, that's the density, right? That's mass per unit volume. So if I multiply the mass per unit volume times some little section of volume, like in the string that we had in the previous example, then I'll have some little element of mass, right? That's how much mass is in that volume, yes?
Yes.
Okay, so I'll put that in here, and we'll get that, this is really some delta E as well. So delta E is equal to 1/2. Instead of delta M, I'll use this. Rho delta V, omega squared, y squared, that's the displacement. It could also be the longitudinal displacement if we're talking about a sound wave, right? So let me divide this by both sides by delta V, the volume. So I get delta E over delta V is equal to 1/2 rho omega squared y squared. But this, recall from the last section, is just the energy density, right? So this is really just eta that we talked about before. Okay? Also remember that from before that the intensity was equal to eta times the wave velocity v, right? So that means it's equal to eta, which is 1/2 rho omega squared y squared, now times v. So we see that it's proportional to the energy density, right, are proportional to the frequency squared, but also the displacement squared. Okay. The intensity, right, additionally depends linearly upon the velocity. Okay. And so I want to save this result. I'm going to write it over here because I want to consider sound waves again, but I want to look at the pressure as opposed to just the displacement. So I'll write over here that I is equal to 1/2 rho omega squared y squared times v. Okay? Okay, so we're now thinking about a sound wave, right? And before, or last time rather, we had expressed a sound wave in terms of its displacement, right? In the direction of the velocity. And it looked something like y was equal to, call it y naught, the maximum displacement, times the cosine of kx, that's the wave number, times the distance in the x direction, minus omega t. Now don't be confused here, right? Y is in the same direction as x, okay? I could have called it s or something else, but that might have been a little less confusing, but a little late for that. I've already drawn the picture here. So as you can see, if I look at the atoms in the material, so let's think this is like a sound wave in some rigid rod, okay? Steel or something like that. We can think of the atoms at each of these sites, right, and the kind of displacement that they're undergoing, okay, as we move along through the rod. And you'll notice that where the separation is large, where the displacement is large, the pressure would be low, right? Because if things get spaced farther apart, this is like where it used to be, this is where it is now, right? Yeah. So as things get spaced out farther apart, the pressure decreases, right? Whereas when the spacing from its displacement is small, the pressure is high, right? So we see that there's this kind of phase difference between the pressure and the displacement, okay? And so if we were to write the pressure equation, it would look something like this. The pressure, as a function of time, right, would also be proportional to a cosine. It would be some P naught, some maximum pressure, times the cosine of kx minus omega t plus 90 degrees, okay? That's because it's a little bit out of phase, or it's 90 degrees out of phase, actually, okay? So it's just because of this relationship between when the pressure is high, the spacing, right, the change in spacing is small, okay? Does that make sense? Yeah. At least conceptually, you see the idea there? Right, so when the spacing is small, our equation for y, the displacement, right, these values would be small. But the pressure is high because it's very compressed, right? When you squeeze it, the pressure goes up, yes? Yeah. Because it's pushing back. It's like a spring, right? Pushing back with that spring force. So, I mean, don't get too hung up on it, right? This is not essential for understanding, but I'm just showing you how I'm doing what I'm doing here, okay? So who remembers what the waves, actually let me show one more thing here, okay? If I were to look at delta y over delta x, okay, because we're going to need that result. Do you remember what that looks like? Right, we're on a cosine, so we're up high, so we're writing down, right? So the velocity is decreasing, right? And it's negative, right? So it's like going downward. Yes. Do you remember all that, right? And so we reasoned that this is really like minus y naught times k times the cosine of kx minus omega t. Yes? Yeah. Okay. So we'll need that result, so I'm just going to hold that off to the side here, okay? But does anyone remember what the formula for the wave speed in a solid is? Remember, the wave speed in a string was the square root of the tension divided by the linear density. Does anyone remember what it is in a solid? Like for air or water or something like that. No? Well, the velocity right, is equal to the square root of the bulk modulus divided by the density, rho. Yes?
Yeah.
So another way to express that, right, is to say that rho, excuse me, not rho, B, the bulk modulus, is equal to rho times V squared. Yes?
Yeah.
Okay. And remember what the definition of this is, right? It says that the pressure, right, so bulk modulus is a little bit like Young's modulus. It's stress over strain, but the stress is just pressure, right? That's force divided by area, right?
Yeah.
So this is equal to minus B times delta V over V, right? It's because the pressure divided by this is equal to the bulk modulus, so I'm just solving for the pressure, right?
Yeah.
Okay? So we're going to assume we have a form for a pressure wave that looks like this, okay? So I can substitute in, though, for the wave speed, right? Because I know what B is, right? So that's going to be minus rho V squared delta V over V. Well, this is equal to minus rho V squared. Delta V and V I can express in terms of their cross-sectional areas, right? Which are going to cancel, of course, right? So that's the cross-sectional area times this distance here. So it's either the delta X, right?
Yeah.
The change in volume, right? The volume is this dimension here, this delta X, right? X2 minus X1. So let's call that delta X, yes?
Yeah.
And the change in the volume is this delta Y you see here, right? So Y2 minus Y1, that's delta Y. That's the change in the volume, yes?
Yeah.
And the areas, they cancel because it's the same cross-sectional area throughout. And now I need this expression that I got here, you see? Which we talked about before. So I can put that in. So this is equal to minus rho V squared delta Y over delta X. Well, it's just this. Minus times a minus is plus. We get the Y naught. We get the K, the wave vector from this. The cosine of Kx minus omega t. Yes?
Yeah.
Okay, so I seem to have made a mistake here. Now that the battery's changed out, we can find it. And I see the mistake already. It's this right here. The delta Y over delta X, right, is sine. Remember how it went? So the position of the traveling wave was maybe a cosine, then the velocity is a sine, and then the acceleration is a cosine again. You remember that?
Yeah.
Yeah. Okay? So I can now show you why this is the case. Okay? So this is delta Y over delta X, which means that we should have this here, sine, okay? But this is the same thing as minus Y naught K. Do you know why they call it a cosine? Just out of curiosity?
No.
The co is for complement, okay?
All right.
So if we take the complementary angle for the sine, we can write it in terms of a cosine, kx minus omega t plus 90 degrees. You see that?
Yeah.
Okay? So that means that I can write this the same way. So I can replace sine. Did I erase my k? I did. With a cosine, but plus 90 degrees, right? So kx minus omega t plus 90 degrees, right? And let's compare that with this equation that we wrote at the beginning, right? So if we were to write out the pressure generally, right, as a cosine with this 90-degree phase shift in it, what would we get? We would get that P equals P naught times the cosine of kx minus omega t plus 90 degrees. Yes?
Yeah.
Could write as pi over 2, but that's fine. So what does that mean? That means that this stuff here is equal to P naught, right? So P naught is equal to rho V squared Y naught times K, the wave vector. So we have we have V squared here, right?
Yeah.
So I'm going to have it just be V to the 1 power times KV. You see that? All right, so I just moved one of the velocity components over here. And the reason I did that is because remember that omega over K is equal to V, the wave velocity, right?
Yeah.
Which means that K times V is equal to omega. So I can take this term here and replace it with the frequency, omega, which then allows me to solve for Y naught, right, in terms of P naught, right? So let's do that. So that gives me that Y naught is equal to P naught divided by rho V omega. Okay?
All right.
Nothing fancy going on here. So why did I want to do that? Because I want to replace this Y naught with this Y up here in this intensity formula, okay? And we'll just do it up here, I guess. So the intensity, which we saved for later, remember that?
Yeah.
We can rewrite as 1/2 rho omega squared times v times y squared. Well, y squared is p naught squared, right? Over rho squared, v squared, omega squared. Yeah? The omega squareds cancel, so get rid of that. One of the v's cancel. One of the rho's cancel. Right? So what do we get here in the end? We get 1/2 p naught squared over rho v. Okay, so we have an expression for the intensity in terms of the pressure now. Okay, now why do I do that? Well, because I want to talk about sound and what happens when you hear a sound. What's going on in there? You've all been on airplanes before, yes?
Yeah.
You ever have your ears pop when you went up to altitude?
No.
You ever have your ears pop when you dive in the water?
Yeah.
You go down to about 10 meters and you feel a lot of pressure in your ears, right?
Yeah.
Yeah, our ears are basically pressure sensors. They're very sensitive pressure sensors, okay? So the kind of the limit of sound that you can hear, right? Or like what's the softest sound that a human can hear? And it's about a picowatt per meter squared. So let me, we've got this formula. We don't need this anymore. So we just wanted to get an intensity equation in terms of the pressure so we could talk about sound and sound waves and what you hear, right? So the limit, the range, a barely audible sound, right, so we'll call it barely audible, is about 10 to the minus 12 watts per meter squared. That's a picowatt per meter squared, okay? The pain threshold, we'll call this pain, is about 1 watt per meter squared, okay? That's a terrible. 1 watt per meter squared. That's a pretty big range, right? It's going from 10 to the minus 12, which is a lot of zeros, right?
Yeah.
To 1. Alternatively, we could have define this as 1, but then we have to make this a 1 with 12 zeros behind it, right? So they're really vast range. And oftentimes when we have big ranges like this, it's true for earthquakes as well, we use a logarithmic scale so that it maps more directly and easily onto human experience, okay? So how does that work? Well, we'll call it beta is kind of the intensity, but the logarithmic version of it. And it's 10 times the logarithm, base 10, of I over I naught, where I naught is some base. I naught in this case would be the barely audible frequency range, okay?
All right.
So this is what we use as our baseline for that. So let's convert these two intensities into decibels, okay? So the barely audible case, right? So beta for, I'll just put an arrow down for low. It's 10 times the logarithm of, well, it's this divided by itself, so that's 1, right? So 10 to the 1 power, right? What is this equal to? This is 0 decibels, right?
Yeah.
So that's our baseline here. This is 0, looks like theta. 0 decibels. All right, what about the pain threshold, right? So beta for pain, call this beta naught, there we go. Beta is 10 times the logarithm of, well, it's 1 divided by 10 to the minus 12, right? So that's 10 to the 12. Well, that's an easy question to answer, right?
Yeah.
What is logarithm base 10 of 10 to the 12? It's asking what power do I have to raise 10 to in order to be equal to 10 to the 12?
12.
12, right, yes. So log base 10 of 10 to the 12 is just 12. So this is equal to 10 times 12, which is equal to 120 decibels, okay? So 120 decibels. Yes?
Yes.
So this is the range, right, for barely audible, 0 decibels, up to hertz to listen to, 120 decibels, okay?
All right.
Yeah. So like a big truck going by, or maybe a freight train, something like that, you're looking at like 90 decibels. Jet plane, close up, taking off might be like 120, maybe 130, 140 decibels, okay? A rocket ship taking off, if you were like right next to a rocket ship, it's like 180 decibels. It would probably make your ears bleed. It would make the rocket ship fall apart, right? Well, maybe not fall apart, but it would do damage to the rocket ship just from the acoustic vibrations, the sound, okay? That's why they pump all that water in when the rockets take off.
Yeah.
You see them pumping all the water in. They have this like hole in the ground, and they throw water. They pump water in at a huge rate, like a swimming pool a second or something like that. and as the rocket is taking off, that water is actually an acoustic dampener. Okay, it softens the acoustic wave, so it doesn't reflect up. Those acoustic waves don't reflect up and damage the rocket as it's taking off. Okay, so those are the ranges. There's a huge difference between 120 and 180. Okay, because this is a logarithmic scale, right? I mean, if between 0 and 120, there are 12 orders of magnitude, right, difference. So you can see that the small differences on this scale actually are significant. So let's look at a fun example of a rock concert, okay? So let's imagine that we've got, our stage is here, and we've got, a bunch of speakers. And I'm not exactly sure what, rock concert power output is, but I'm going to guess that it's about 1,000 watts. And that's pretty loud. Let's also suppose that the musicians are 10 meters away, okay? So that means the front row is here at 10 meters away from the speakers, right? And the back row, let's assume that it's 100 meters, so it's about a football field length away, right? So here's the back row at the stadium for people to witness the rock concert, 100 meters. So if these are 1,000 watts of output power for their amplifiers, right? What is the intensity? How many decibels is that going to translate into for sound here at the front row of the audience, right? And so we can calculate that. So we say I is equal to 1,000 watts. Again, these are speakers, so they're not going to radiate the sound energy in a spherical fashion. They're going to radiate them in kind of a hemispherical fashion. So at least we can approximate that as a hemisphere. So we'll divide that by 2 pi r squared. Okay, so in this case, r is 10, so r squared would be 100, right? So it's 2 pi is approximately 6. This is going to be like 1.6 or so, but we're just going to, for ease of argument, say it's approximately equal to 1. Okay?
Right.
In reality, it's more like 1.6, right? Because 1,000 divided by 600, 1.6, right?
Yeah.
But we'll say this is approximately 1. That's a terrible approximately sign. Approximately 1. And so how many decibels is that going to be? Well, we already kind of know that, right? If we calculate the decibels, right, beta, that's equal to 10 times the log of 1 divided by 10 to the 12, so that's 10 to the 12, right? So that's just 120 decibels. So if you had a 1,000 watt amplification at your rock concert, the people in the front row would be just at the pain threshold, okay?
All right.
What about the people at the back, right? Let's see what they would be in for, provided we don't have booster speakers spread around somewhere, right? So here, the intensity would be the 1,000 watts of power generated up here, divided by 2 pi times 100 meters squared. So that's times 10,000, right? 100 squared. And that's going to be like 1 times 10 to the minus 2, approximately. It's going to be 1.6 times 10 to the minus 2, but we'll call it approximately 10 to the minus 2, right? So what does that give us for decibels, right? What's the, how loud is it back there, right? Well, it's 10 times the log of 10 to the minus 2 divided by 10 to the minus 12. That's the same thing as 10 to the minus 2 times 10 to the 12, which is 10 to the 10. So that's 10 times 10 is 100, so that's 100 decibels, right? Is that loud? Well, yeah, it's pretty loud. It's not the worst thing in the world, but 90 decibels is like, really loud traffic or so. So, anyways, so there's a rock concert and the sound levels. Okay?
All right.
Any questions about this? Yeah? Just the takeaway, basically, we defined a couple of new terms, the energy density and the intensity, right? The energy density is the energy per unit volume. The intensity is the energy, the power per unit area, right?
Yes.
And we said that the energy can be related to, the energy of just a standard harmonic oscillator, right? So just a mass on a spring kind of system. So the energy is proportional to the frequency squared, and it's proportional to the displacement squared, okay?
I thought power was energy per unit area.
Power is energy per unit time per unit area, okay?
Okay.
No, that's it. I'm sorry. Power, now you're getting me confused. Power is energy per unit time, okay?
All right.
Make sense?
Yes.
So it's how much energy you produce or consume during a given interval of time.
All right.
Intensity is power per area, right?
Yes.
Yeah. So when you think of intensity, think of the sun, right? How much energy or how much power is getting dumped into every square meter on the surface of the Earth, right?
Yeah.
From the sun. Yeah. And the sun is 93 million miles away. I mean, you can feel it, right? When you put your hand, you feel it's warm, right?
Yeah.
to feel those sun rays. So, so it's a lot of power. Did I erase it already? Yeah, it's roughly 1,350 watts per meter squared. Yeah, if you could build a solar cell that could capture 100% of that, it'd be pretty good, right?
Yeah.
So, yeah. So we got these definitions. We related the energy of a wave. It's related to the energy of an oscillator, right? So we just think of each of the individual sections of the wave that's going up and down or compressing in and out, right? We know what that energy is, right? That's just this, the parabolic energy that we drew, right? When we talked about oscillating springs, yeah?
Yeah.
So it's parabolic or quadratic, however you want to say it. And then finally, we went through some of the ugly details of how to relate the displacement of a longitudinal wave. That's how we did it last time in terms of displacement. How do we translate that over into pressure, which we did. It's not pretty, but we got the result so that we could then use it to talk about acoustics, sound, decibels, right? Our perception of sound, which is when we hear things. So you hear a loud noise, you're probably not thinking, oh, wow, it's a lot of intensity or a lot of power per unit area, right? That's probably not what you're thinking. You just think it sounds loud. And so decibels is a scale that maps onto sounds loud, but of course that can be mapped back onto a scale for intensity, which is a much wider range, right? The numbers are drastically different, right?
Yes.
Okay. I mean, remember, like this 1 watt, excuse me, 1 watt. Yeah, 1 watt per meter squared, right? Put that on the background of 1 atmosphere of pressure, right? We're at atmospheric pressure, right? That's like 100,000 watts per meter squared, right?
Yeah.
Sorry, it's not power. It's the pressure. So if you were to calculate what this pressure is, it's rather small. This is the intensity. But this pressure is a rather small pressure in comparison to the 100,000 pascals. Sorry, misspoke. Pascals that we get from atmospheric pressure. Okay.
Okay.
So, anyways, that's all I've got on that. Any other questions other than about power?
No. Well, what is B?
It's beta. That's just decibels. I use beta. I think it's standard, but beta for decibels, if you want. Okay. If this is just the intensity, but on a decibel scale, right? This formula right here, 10 log of the ratio of the intensity to some, reference point. And the reference point is barely audible. Okay.
Okay.
Make sense?
Yeah.
Okay. All right. That's it.